Alright class, today we're going to try to graph this pretty nasty little function. And when I say graph, I mean we're going to do the works. We're going to find the critical points, figure out if they're maxes, mins, do the second derivative test. Not second derivative test, but find the second derivative and find the inflection points and then try to put it all together. Now before we do that, let's just think a little bit about this thing. This is comprised of two functions. We've got our x to the 2/3, which I've lovingly referred to as the kindergarten bird, and it sort of does something like this. See how it looks like a kindergarten bird? And then the other function we have is x minus 4 squared. That's a parabola. It's got a vertex at 4, 0, and it's going to look something like that. So together, we're expecting a graph that has this part to it, this part and this part sort of stuck together. That means it's probably going to have a maximum before it gets to that minimum, but it's going to have a minimum there, it's going to have a minimum here at this cusp. And because if I look at the degree of this thing, it's going to have a degree that's bigger than 1. That means it's going to eventually have to be on this side of the cusp. It's going to have to go concave up. So we're expecting an inflection point over here somewhere, and probably an inflection point between the maximum and the minimum we're going to have there. Alright, so we're expecting 2 mins. Maybe this graph is upside down or something too, so we don't know yet. But that's sort of what we're going to expect. Okay, so let's get busy with the derivatives. Okay, so we use the product rule on this thing. We get 2/3 x to the negative 1/3. Okay, that's the derivative of x to the 2/3. And then we would leave x minus 4 squared alone. Alright, so then plus, we'll leave x to the 2/3 alone this time. And then it's 2 x minus 4 to the 1. Alright, and what we're going to do is we're going to factor stuff we know out. And this is typical with ones that have a negative fractional exponent and a positive fractional exponent. We're going to factor that out. Okay? So, let's just talk about how that's going to happen. So we're going to have 2/3. Oops, sorry. We're going to factor a 2 out. We're going to leave a 1/3 with that. Okay? So we're going to have 2 x to the negative 1/3. And we can also factor out an x to the x minus 4. Okay? And what we'll be left with is 1/3 x minus 4 out of this. Okay, and clearly the 2x minus 4 factors, so we're left with x to the 2/3. What do we get when we factor an x to the negative 1/3 out? And here's how we can sort of think about that. You would have x to the negative 1/3 times x to the, I'm not sure, that's what's going to be left over. And if you multiplied it back out, you should get x to the 2/3. So that means, exponent-wise, negative 1/3 plus my question mark is going to equal 2/3. And some simple math there will tell you that the question mark has to be 1. So we're left with just x. Alright, let's clean this up a little bit. Okay, so this is going to be, let me just write it above, that's going to be 1/3 x minus 4/3 plus x. So that's going to be 4/3 x minus 4/3, which I can factor a 4/3 out of, and I'll stick that out front. Oops, thirds. So 2 times 4/3 is going to be 8/3. X to the negative 1/3. X minus 4. And x minus 1. Okay? Now, critical points. So that would be places where the derivative doesn't exist or where the derivative is equal to 0. So in theory here, we're thinking about setting this thing equal to 0. But we get x equals 0 from the negative exponent because that means f prime of 0 does not exist. And that's one of the ways you get a critical point. And that always happens when you have fractional exponents that are between 0 and 1. All right, the other two, when we get set things equal to 0, we're going to get. So we're going to get the x equals 4 and x equals 1 from that. And when it's in nice factored form like this, it's really easy to do a sign chart. I really wouldn't want to have to do the second derivative test on this thing. It might not be too bad, but... Okay, so when I plug something negative in, all three terms are negative. So that means negative. Well, this is for f prime. When I plug something between 0 and 1 in, that term's going to be positive now, but those are going to be negative, so that's going to be positive. And when I plug something between 1 and 4 in, that's positive. The negative 1, x to the negative 1/3 is positive, but that's negative. And lastly, when I pass 4, all of them are positive. So that means we're expecting a local min here, a local max here, and a local min there. Okay, so that's what our first derivative test tells us. All right, the second derivative, deep breath. Okay, so for the second derivative, I think it's going to be, I'm going to rewrite f prime, and let me get a clean sheet of paper because this is going to take a little bit of room. So for the second derivative, let me copy down what f prime is supposed to look like here. I'm going to go ahead and I'm going to take this part and I'm going to multiply it out. I don't want to have 3 terms multiplied because then I've got to do this triple product rule kind of thing. So I'm just going to multiply that out because that's a polynomial. It'll be easy enough to handle like that. So that's going to give me 8/3 x to the negative 1/3 and x squared minus 5x plus 4. Okay, so that's what f prime is when I multiply all that stuff out. And now what I'm going to do is I'm going to go ahead and take a derivative. Alright, so let's see. So negative 1/3 times that's going to give me negative 8/9 x to the negative 4/3 and then x squared minus 5x plus 4 and then plus 8/3 and the derivative of that's just 2x minus 5. Okay, so a couple things to note here. I'm going to, and I also left off the x to the negative 1/3. Okay, so I'm going to factor out the largest negative exponent, so x to the negative 4/3, and that's going to leave me with an x there. I can factor like an 8/3 out, but I have this extra third. So here's what I'll do. I'll factor an 8/9 out of both terms, and I'll have to multiply this one by 3. So 3 over 3. Okay? So, alright, so 8/9 x to the negative 4/3. Okay, so that minus sign stays with all of those. So those, it's going to be negative x squared, and it's going to be plus 5x minus 4. Okay. All right, and we said we were going to have to multiply by 3 over 3. That means there's a 3 that gets stuck here. And when we factor the negative x to the negative 4/3 out, that's going to be just x to the 1. So 3x times 2x minus 5 is going to give me 6x squared minus 15x. Okay? Alright, and one last simplification. So 8/9 x to the negative 4/3, and we're going to have 5x squared minus 10x minus 4. And look, for the record, I would officially say that is not a nice function, not a very pretty thing. It's not going to factor very well. So we know that this is going to give me x equals 0, but we also know from what we did up here and from what we know about the kindergarten bird that it's going to be a cusp. So it's going to be a minimum, so it's not really going to be an inflection point. There's not going to be a sign change there. And that makes sense because the numerator of that exponent's even. So I would eventually be raising whatever this is to the 4th power. So that's going to be positive on both sides. So that's going to be neither, and we can talk about that in a second. Okay. This, however, let's see. So if I do the quadratic formula, b squared, and let's see, 4 times 4 is 16 times 5 is going to be 80, and that's negative, so we're going to have to say plus 80. Okay, so this is 10 plus or minus root 180 all over 10. Okay, so let's just think about that for a second. So 180, the closest perfect square, that's 196. So this is slightly under 14. So that's about 24 over 10, so roughly-ish 2.4. Okay, and you can get a calculator to get an exact value for that. And then the negative one, which we expected we were going to have a negative one, so that's going to be 10 minus 14 and over 10, and that's going to be like, what, 4/10 or 2/5, so negative 2/5. Okay, so we do get the two answers that we're expecting. Okay, and if we did a sign chart for the second derivative, oops. Okay, so I'm going to put my minus answer there. We'll put 0 here, and we'll say the positive one's here. We said that would be no sign change there, but these are that's a parabola pointing up, and it has 2 zeros, so it's going to change sign between them. So sorry. So when we plug stuff in, what are we going to see? Well, we know we're going to have everything's going to be positive over here. And we know it's supposed to change sign, so it's going to be negative, negative, and then positive there. Okay? So that's what our signs are going to look like. That means we have an inflection point there and another inflection point here. Okay? And lastly, we would want to maybe find y values for all these. I'm going to leave off the inflection points. We'll talk about where they are in a second. But if I find y values for the 3 critical points that I had, so that's substituting things back over here into this thing. So if I plug 0 in, I'm going to get 0 and then whatever. And if I plug 4 in, I'm going to get 0 there and then whatever. And if I plug 1 in, I'm going to get negative 3 squared with 9 times 1 to the whatever, so just 9. Okay? So the 3 points of interest are 0, 0, 1, 9, and 4, 0. Okay, and so when we sketch this thing, okay, there's our 2 zeros. There's our 2 zeros there. And we have our cusp here, which is a minimum. And we have our minimum here. And way up here, I'm not going to count all the dots out, the hash marks out, but that would be 1, 9. Okay, and this thing is going to start out being concave down, as we can see, concave down on the right side of 0. Okay? So it's going to come up here to this maximum, and then it's going to come down to that minimum and then go up. Okay, now somewhere in the middle here, that's where my 2.4-ish x value was, and the y value is somewhere between 9 and 0. Okay, it's kind of hard to see it, but it does switch from being concave down here to being concave up for that minimum. Then out here, it's supposed to sort of be looking like sort of a root curve. But once again, because the limit's going to be infinity as x goes to negative infinity, so it's going to have to bend back up. And I know scale-wise this is not perfect, but this is where that negative 2/5 point is. Okay, so somewhere over there is where the curve switches like that. So, in a nutshell, that is the graph of that function. All right, have a nice day. Toodles.